My name is Kimball. I'm from the University of Dayton in Dayton, Ohio. Obviously, I'm presenting on code integration-based vulnerability auditing. The primary purpose of this talk is to release a new tool called Levi. Levi does many things, but two of which are it does import and inline hooking. Okay, so the outline of this talk, basically I'm going to tell you the motivation behind this research, introduce Levi, tell you briefly the implementation, and then go through a couple case scenarios to give you good examples of really how this thing works. So the motivation behind this research was some of these tools didn't do everything which I needed them to do when I was looking for vulnerabilities. How many people have ever done API hooking? Show of hands. Okay, import hooking, something like that. These tools are code profiling tools so you can analyze closed source executables or binary files. It's the process that you have to perform in closed source software to find vulnerabilities. So what these tools at the top do, like API Spy 32 and API Monitor, is that they actually hook API calls like string copy, sprintf, wsprintf, all the functions that we find are vulnerable that lead to these exploits that are being released. Bug Scam is a set of IDC scripts for IDA which attempts to do the inline hooking but doesn't do anything for you at runtime. So Levi is a tool that I developed. It's a code profiling tool. It's a command line tool for the Windows NT family. And basically it does two things, inline and import hooking, and it does those statically or at runtime. It also supports things like multi-byte and Unicode character sets. So here's what it looks like at a high level statically. Whatever you're auditing, serverx.exe, any type of PE file, it can be a DLL or system file. And it produces two files suffixed with imports.dat and inlines.dat. And then the runtime analysis is really what is useful here. It takes those two files, the two static files, and then at runtime, when the user's using the program, or whenever, if you're using it, it'll create two files, runtime imports and runtime inlines.dat. So I implemented this, the import hooking. I'm not going to talk about import hooking here. It's been done. If you want references, you can read Windows 95 System Programming Secrets by Matt Petrick or some other book, the Shellcoder's Handbook. So I'm not talking about that here because it's been done. What I haven't seen done is the inline hooking technique to monitor buffers that are actually being processed insecurely inline in the text section or in your code section. And that is what I'm going to concentrate on here. There's two different techniques that Levi allows you to use to watch those. One's entry point obscuring, which I'm calling move point obscuring, which I'll explain in a second. And then the other is, of course, code integration. So you may be asking, okay, I know what an import function looks like, string copy or wsprintf or something in the Windows API, but what are these inline code constructs that you're actually monitoring for? Now, I'm sure most of you know that compilers don't generate the same binary executable, so it'd be a pain to create some really big signature database of all these insecure functions compiled down with all these different compilers. So what I attempted to develop was a pattern matching technique by cross-referencing using different compilers and compiling all of the vulnerable functions like string copy and sprintf. These are just two examples, and find out what they have in common, what's similar between all these things. What are we looking for when we actually disassemble an executable? So, and other requirements are, okay, if the user writes his own code and doesn't use an insecure function or writes an insecure sorting routine, you want to be able to watch those buffers at runtime as well. So some of the rules for the pattern matching technique are there a small cycle, there has to be a conditional branch, it has to be moving from memory to register to memory, etc. There's a whole bunch of them. That's beyond the scope of this presentation. Okay, so how it does this, entry point obscuring, which I'm calling move point obscuring here, it's a virus infection technique that basically obscures the entry point to your actual function that you're watching, so it jumps somewhere else in memory, like a detour function. And then it executes your own code and then jumps back into regular execution. Obviously, there's things that you have to do to make that actually work at runtime. But anyways, basically what this does is it jumps to the logger function, it logs all the buffers and things that you need, and then fixes the actual MPO point, and then obscures branches any exit point out of the cycle, the loop that you're actually watching for. And this is what it looks afterwards, where the jump post obscure is. And then once that gets called, you actually fix all the local branches just like you fix the MPO, and you repeat the MPO process. So this is one of the two techniques I use to actually be able to monitor those buffers at runtime using the pattern matching technique. So there's a problem with MPO that's not usually addressed with EPO because you're usually overriding the function epilogue. But here we're actually overriding the first move instruction within our code construct that's found by the pattern matching technique. So what happens is if you have a jump instruction that's 5 or more bytes, it's going to overflow the instruction that you're overriding if it's less than 5 bytes. So here you see that the first 2 bytes, 4040, is actually overriding the next instruction. And what happens if execution branches to that instruction is arbitrary execution is going to occur, and the thing's most likely going to throw an exception, not handle it, and crash. So one possible solution to this is code integration. Basically, code integration, unlike entry point obscuring, is you're not actually overwriting any code in memory, but you're making room in memory and expanding the text section or the code section and making room for the code. And one of the first examples was in Zombie's Mistfall engine. So at a high level, what this looks like is you obviously have to disassemble the PE file, then you merge your code wherever you want with the existing code, and here we're doing the jump logger, and then recalculate all the addresses. Obviously, if you're going to move code around, all of the relative virtual addresses and virtual addresses point to a certain location, and that's how the program executes, so you have to fix all those. And things to consider when you're fixing those is if you have relative 8-bit addresses from negative 127 or 128 to 127, you have to change all those to 32-bit addresses if they go outside that range. So there's certain things to think about. But once that actually settles, that merge settles, then you have 2 code sets not recompiled but in the same actual text section. So let me demonstrate to you how Levi works. Basically, here's what it looks like. There's several options. You can check the buffer size of the inline code construct, or you can't check it. Let's get to... Okay, so if I ran Levi against an executable, all I would have to do was say Levi, give it /d for the dynamic runtime analysis, and then give it the PE file name. So it's really easy to use. What it's going to do is it's actually going to produce those 2 static files and the 2 runtime files. And I actually already ran it against Movie Maker. It takes a few minutes, which I don't have time for right now. So I already did this. And we're going to look at the import functions. So this is that API hooking technique. And you see that, okay, string copy in secure is being called with this buffer at this address at this location in memory. And it gives you all of those at runtime. I'm not talking about that. What I am talking about, which I already ran against Outlook, are the inline functions. So these are all the inline functions similar to the import functions that are being monitored at runtime. So what you can see here in the very beginning are all of the actual environment variables of your process when it's running, the address where they're being processed right here, and then the actual address in memory where those buffers are. So what does this give us, right? How does this help us find vulnerabilities in closed source software? Well, because we're using a pattern matching technique that came from a whole bunch of insecure functions like string copies, printf, wsprintf, etc., most likely there are false positives. These buffers, if they can be input by the user or some other source, they can be vulnerable. So let me show you an example in the VPN interface of connectivity. So basically, I already attached Levi to this. I actually didn't attach it to the executable, but I attached it to one of its DLLs, msvcrt.dll, because that's where a lot of vulnerable functions lie, so it makes sense, right? So we're going to go ahead and run this, and obviously I don't have my interface on, but we couldn't VPN to blackhat.com. But we don't need to go further than that to do an analysis of this program to find a vulnerability. Because what we're going to do is we see here it produced the imports runtime file and the inlines. So we just open up the inlines and we actually look at the buffers that are being processed insecurely. And if we scroll to the bottom, we see that, okay, www.blackhat.com is being processed at this address. And this address, if we look at the static inlines, is a vulnerable string copy type of code construct, and it's looking for a null byte. So what we can do is write the shellcode like any other exploit and go to connect again, and then we pop a shell. Right? And this one just happens to be running at system level. Now, it's a proof of concept, but the point is that Levi actually showed us the buffers that are being processed insecurely. So you could run this on a larger application, or you can run this past authentication and see what's going on actually as the session occurs. So let me show you another example. This is a TFTP DHCP server, and we're going to run it. What we're going to say is TFTP, my loopback address, and we're just going to do a git on Black Hat test file, a little file that I created. So it says transfer successful, right? And we get the output here. Now what we're going to do is we're going to actually look again at the inline file that Levi created, and we see again all the environment variables being processed in the beginning. But when we go to the bottom, again, it shows us Black Hat test file.exe is being processed on the server at address 77C460AD. There's no messing around, no manual auditing, no disassembling and searching through thousands of lines of code. This shows us exactly where the problem has occurred. So again, what we can do after we rerun the server, I already created the actual shellcode. TFTP 127 git, and then our shell, 14-byte shell in the beginning, and it popped the shell. When we exit, it crashes the server. Now what's cool about this, after you do that, is you actually can go back into the inlines file, again, because when you actually exploited the server, it's still running and still monitoring all those buffers. Oops. And we see at the very bottom, because once the server crashes, obviously it's not running, so one of the last things that should have happened is it processed the exploit that we sent it, which it did. At the very bottom here, we see our shellcode in all the A's and in the return address. So even if you don't want to search for your own vulnerabilities and use this tool as a code profiling tool to do that, you can attach it to a server, and then there's a good chance if someone exploits you and it's a buffer overflow, when your server crashes and you think, okay, well now how do I find out what happened? You go to the inline file and scroll all the way down, and the exploit of how that person attacked you is going to be right there. At that point, you can just reverse engineer that, and you have something to actually show what happened. So anyways, thanks for listening. Go to www.layerdefense.com/Levi to download the latest version. 01's on the CD, I think, and this is 04. So I fixed a few things. But please give me feedback. Let me know what you think needs to be added, how we can improve upon this. But I think this, after fuzzing goes away and we have to resort to lots of manual auditing, inline hooking like this is going to be the way to go. So let me know what you think.